All right, let's take a journey to the absolute edge of human knowledge. We're going to tell the story of the universe, but, not the simple one you might have learned in school. We're talking about the version that has today's greatest physicists completely stumped. A story that pushes our most fundamental ideas about reality right to their breaking point. So let's just dive right in with the biggest, most mind-bending question there is. What was here before the beginning? For the longest time, that felt like a question science just couldn't touch. But now, we're starting to get some incredible and honestly pretty wild clues. The story of the universe almost always kicks off with the Big Bang. This idea of a single, infinitely hot, infinitely dense point that held, well, everything. But it turns out, the story you think you know, it's not the whole story. Yeah, this is the classic picture, straight out of Einstein's playbook. 13.8 billion years ago, bam, the universe just explodes into being from this single point, a singularity. It's a powerful image for sure. But what modern science is telling us now is that this wasn't really the beginning. It was more like the aftermath of something even crazier. And this brings us to the cosmic prequel, a phase we call cosmic inflation. And I really want you to focus on that one word, before. This happened before that super hot, super dense state that we call the Big Bang. The universe was already expanding, and it was doing it at a speed that is just impossible to imagine. So try to wrap your head around this. In a fraction of a second, we're talking a trillionth of a second. A patch of space smaller than a single atom, inflated to become bigger than our entire known universe. And then, just as suddenly, it stopped. All of that incredible energy that was driving the expansion got dumped into space, superheating it and literally creating the first particles of matter out of pure energy. That incredible, hot, dense moment, that's what we now see as the Big Bang.
Okay, so inflation sets the stage for the universe. But what are the rules of the game? What laws govern everything that just popped into existence? For that, we have to look at what is probably humanity's most successful scientific theory ever. We call it the standard model of particle physics. And look, it is an absolute triumph. For about 50 years now, it has described the basic building blocks of our world and the forces that govern them with just stunning, unbelievable precision. And here's the cast of characters for reality. On one side, you have the fermions. These are the particles of matter, the quarks that build protons and neutrons and the leptons, like the good old electron. Then, on the other side, you have the bosons. Think of them as the force carriers, the messengers, like the photon, which carries light, or the gluons, which literally glue atomic nuclei together. You really can't overstate how successful this model is. It ties together 3 of the 4 fundamental forces of nature. It predicts the outcome of insanely complex particle experiments with pinpoint accuracy. It even told us the Higgs boson had to exist decades before we actually found it in 2012. It really is the theory of almost everything.
But there's a catch, isn't there? And it's a huge one. There's a reason we have to say almost everything.
Because the second we step back and look at the universe as a whole, we run into these massive, profound mysteries that the standard model has 0 answers for. These are the deep cracks running through our otherwise beautiful theory.
And the list of what it can't explain is, well, it's pretty humbling. For starters, how about gravity? The most obvious force in our lives? Yeah, it's not in there. It says nothing about dark matter, the invisible stuff that's holding our own galaxy together. It has no idea what dark energy is, this mysterious force that's accelerating the expansion of the entire universe. It also can't explain why we're even here, why matter won out over antimatter at the very beginning.
And this chart really puts that failure into perspective. Everything the standard model describes, every star, every galaxy, every person, is all crammed into that tiny little 5% slice called normal matter. Think about that. Our greatest, most precise theory of reality only describes 5% of it. We are fundamentally clueless about 95% of our own universe. Now, that problem with gravity is especially thorny. See, modern physics really stands on 2 giant pillars. You've got general relativity, Einstein's theory of the very big, like planets and galaxies, and you've got quantum mechanics, the theory of the very small, of atoms and particles. The standard model is built entirely on quantum mechanics, but it is completely, fundamentally incompatible with general relativity. The 2 theories they don't speak the same language.
And this clash of titans, this conflict between our two best theories, leads to some truly spectacular failures. And none is more spectacular or more spectacularly wrong than something called the vacuum catastrophe.
So, according to quantum mechanics, what we think of as empty space isn't empty at all. It's actually a seething, bubbling foam of virtual particles that are constantly flashing in and out of existence. All this activity gives empty space a kind of baseline energy, of vacuum energy. And we can try to calculate how much energy there should be.
The problem is, when physicists do the math, the answer they get is so unbelievably wrong that it's been called, and this is a direct quote, the worst theoretical prediction in the history of physics.
So how wrong is it? Our theories predict that the energy of the vacuum should be 10 to the 120th power larger than the value we actually measure out in the cosmos. That is a 1 followed by 120 zeros. There are literally not enough atoms in the universe to write that number out. It is the most wrong a prediction has ever been in the history of science. It's a giant flashing red light telling us we're missing something huge.
All these cracks, all these problems, this catastrophe, they all point toward an ultimate boundary, a scale so fantastically small that our current understanding of reality just completely stops making sense. This is the place where physics actually breaks down.
We call it the Planck scale. It's the absolute shortest distance and the shortest time that has any meaning. Any smaller than that, and both general relativity and quantum mechanics start spitting out nonsense. At that level, the very ideas of smooth space and flowing time might not even apply anymore.
And just how small are we talking? Well, this analogy is just wow. Imagine you could take a single proton, a tiny particle inside an atom, and blow it up to the size of the entire observable universe. On that colossal scale, the Planck length would be about the distance of a flight from Tokyo to Chicago. It's a level of smallness that our brains are just not built to handle. But here's the really cool part. This isn't just a dead end. It's a signpost. Many physicists are convinced that down at the Planck scale, all four of nature's forces, gravity, electromagnetism, the strong and weak forces, all come together and become one single, unified superforce. This is the frontier. This is the realm of some new, undiscovered physics. So where does all this leave us? We've gone from a time before the Big Bang, through the incredible successes and the spectacular failures of our best theories, and we've ended up at the very foundation of reality itself, only to find that it's broken. It's clear the story of the universe is nowhere near finished, and that leaves us with the ultimate question. If our most fundamental laws of physics are failing, what new revolutionary ideas are going to come along and write the next chapter?